Hello, in this lecture we answer two questions. In the first question we find out they are of this given shape. In the second question we find out they are of this square ABCD using three different methods. So we start with the first question. In the drawing we have a circle that is inscribed by this triangle ABC. We know that side AB of triangle ABC equals to 6 units in itself, side AC equals to 7 units in itself, side BC equals to 9 units in itself. Again, our task is to find out the area of this given shape. So first of all, we define this angle ACB as theta. That is to say, angle ACB equals to theta degrees inside according to our definition. So we will implement the law of cosines in this triangle ABC. A bit quicker on the law of cosines. The law of cosines is true in any triangle. This is triangle ABC that could be any triangle. Side AB of triangle ABC equals to A units in itself, side AC equals to B units in itself, side BC equals to C units in itself. This is angle BAC is equals to theta degrees in sides. So in this triangle ABC that could be any triangle, the following, according to the law of cosines, the following equation is true, that cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. Again, cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. So we implement the law of cosines in this triangle ABC. According to the law of cosines, we get that in triangle ABC, the following equation is true, that AC squared plus BC squared minus AB squared over 2 times AC times CB equals to cosine theta. It again, according to the law of cosines, this triangle ABC, the following equation is true. That cosine theta equals to AC squared plus BC squared minus AB squared over 2 times AC times CB. Okay, so this equation is the implementation of the law of cosines in triangle ABC. So cosine theta equals to AC squared. AC is 7, therefore AC squared is 7 squared plus BC squared. BC is 9, therefore BC squared is 9 squared minus AB squared. AB is 6, therefore AB squared is 6 squared over 2 times AC, that is 7, 2 times 7, times BC. BC is 9. So in total, if you found out that according to the law of cosines, in triangle ABC, cosine theta equals to 7 squared plus 9 squared minus 6 squared over 2 times 7 times 9. So cosine theta equals to 7 squared. 7 squared is 49. Plus 9 squared. 9 squared is 81. Minus 6 squared. 6 squared is 36. So in total, the note of this expression, we have 49 plus 89, 49 plus 81 minus 36 over, we have 7 times 9 is 63, 63 times 2 is 126. So cosine theta equals to 49 plus 81 minus 46 over 126. So cosine theta equals to 49 plus 81 is 130 minus 36 over 126. So cosine theta equals to 130 minus 136 is 94 over 126. So in total, if you found out that cosine theta equals to 94 over 126. Ninety-four over 126 is 0.7169. So cosine theta equals to 0.7169. We would like to find the value of angle theta itself, the size of angle theta. In order to find the size of angle theta, we'll operate the opposite function of cosine, that is arc cosine, on the result of cosine theta, that is 0.7169. In this way, we get the value of angle theta itself. So arc cosine of the result of cosine theta, that is 0.7169, is equal to angle theta itself. So angle theta equals to arc cosine 0.7169. You can find using any scientific calculator that arc cosine 0.7169 is equal to 40.368 degrees equals to theta. So in total, we found out that the size of angle theta is 40.368 degrees. What is the value of 180 degrees minus theta? The value of 180 degrees minus theta is actually 180 degrees minus 40.368 degrees. That is actually 139.632 degrees. So in total, we found out that 180 degrees minus theta is equal to 139.632 degrees. In the next step, we'll define the center of this circle. This point is point O. We'll define the point of tendency of tangent BC with this circle. This point is point L. We will define the point of tendency of tangent AC with this circle. This point is point P. We define the point of tendency of tangent AB with this circle. This point is point Q. In the next step, we define the center of the circle as R, and we join points O and N together by a straight line. Point O is the center of the circle, point L is the point of and the circle itself. Actually, point L is the point of tendency of tangent BC with this circle. So point L is the point on the circle itself, therefore OL is the radius of the circle. This goes to R, according to our definition. Can implement here rule 1. Why? Because the radius OL is equals to R. The radius OL is drawn to point L, that is the point of tendency of tangent BC with this circle. And whenever your radius is drawn to the point of tendency, then tangent BC will be perpendicular to the radius LO. If BC is perpendicular to LO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees, is only to rule 1. The next step, we join points O and P together by a straight line. OP is the radius of the circle that equals to R. Point P is the point of tendency of tangent AC with this circle. So according to rule 1, this angle equals to 90 degrees. This angle also equals to 90 degrees. In the next step, we will implement rule 2 in our drawing. I'll finish quickly on rule 2. According to rule 2, the lengths of two tangents from a common external point to a circle are equal. In the drawing, in a circle, this is the common external point, point P. From the common external point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, they are equal to each other. That is to say, PA equals to PB. We can implement rule 2 in our drawing. First of all, we define the length of side BL as A. That is to say, side BL equals to A units in itself according to our definition. In the next step, we'll focus on this common sum point B. For the common sum point B, we have two tangents to this circle, tangent BL and tangent BQ. And according to rule 2, they are equal to each other. That is to say, BL equals to BQ. But BL equals to A, therefore BQ must be also equal to A, because they are equal to each other according to rule 2. BQ equals to A in its length. AB equals to 6. QB equals to A, therefore AQ equals to AB, that is 6, plus QA, that is 8. So in total, AQ equals to 6 pounds of units in its length. Likewise, what is the length of line segment LC? On the drawing, it is very easy to see that LC in total equals to BC, that is 9, minus BL, that is A. Again, LC equals to BC minus BL. So LC equals to BC, that is 9, minus BC, that is 9, minus BL, that is A. So in total, LC equals to 9 minus units in its length. In the next step, we'll focus on this common sum point A. From the common sum point A, we have two tangents to this circle, tangent AP and tangent AQ. And according to rule 2, they are equal to each other. That is to say, AQ equals to AP. but AQ equals to 6 minus 8, therefore AP must be also equal to 6 minus 8, because they are equal to each other according to all two. In the next step, we focus on this common sum point C. For the common sum point C, we have two tangents to this circle, tangent CL and tangent CP. And according to all two, they are equal to each other. That is to say, CL equals to CP. But we just write down how that CL equals to 9 minus 8, therefore CP must be also equal to 9 minus 8 in itself, because they are equal to according to all two. Equal to each other according to all two. It is given as the question that side AC of triangle ABC equals to 7 units in its length. But AC consists of two line segments. AC equals to AP plus PC. Again, AC equals to AP plus PC. AC equals to AP plus PC. So AC equals to AP 6 minus 8 plus PC. PC is 9 minus 8. So in total, AC equals to 9 minus 8, 6 minus 8 plus 9 minus 8. AC equals to 6 plus 9 is 15. Minus 8 minus 8 is minus 2A. So AC equals to 15 minus 2A. AC is 15, according to what is given in the question. So we substitute AC equals to 7 units in itself, according to what is given us in the question. Side AC of triangle AC equals to 7 units in itself, so we substitute AC by 7 and we get that AC is 7, it is equal to 15 minus 2A. 7 equals to 15 minus 2A. Here we add 2A to this equation and we substitute 7 simultaneously, and we get that 2A equals to 15 minus 7 is 8, so 2A equals to 8. Here we'll divide this equation by 2 and finally get that A equals to 8 over 2, that is 4. A equals to 4 units in its length. AL equals to A and A equals to 4. QB equals to A and A equals to 4. AQ equals to 6 minus A, 6 minus A, 6 minus 4, that is 2. 6 minus A, AP equals to 6 minus 8, that is 2. PC equals to 9 minus 8. 9 minus 8 is 9 minus 4, that is 5. LC also equals to 9 minus 8, that is 5. This is sector OLP. What is a sector? A sector is a portion of a circle enclosed by two radii and the arc LP between them. Okay, again. The green shape AOB is a sector. It is a portion of this circle enclosed by those two radii and arc AB between them. The two radii are defined as the legs of the sector. The angle between the legs of the sector equals to theta. What is the area of the sector AOB? The area of the sector AOB equals to the area of the circle that contains the sector, that is actually pi r square, r is the radius of the circle, times the angle between the legs of the circle, that is theta, over 360 degrees. And again, the area of sector AOB equals to pi r square times theta over 360 degrees. In the next step, we'll find out the semi-perimeter of this triangle ABC. What is a semi-perimeter? A semi-perimeter is a perimeter over 2. And a perimeter is the sum of the three side lengths of any triangle. Again, the perimeter is the sum of the side lengths of the triangle. In this case, it is AB plus BC plus CA. This is the perimeter. The semi-perimeter is the perimeter over 2. That is to say, it is AB plus BC plus CA over 2. So what is the perimeter? What is the value of the perimeter of this triangle ABC? What is the value of the semi-perimeter? S is the relation for a semi-perimeter. So S equals to AB, that is 6, plus BC, that is 9, plus CA, that is 7. 6 plus 9 plus 7 is the perimeter of this triangle ABC. And the semi-perimeter is the perimeter over 2. So S equals to 6 plus 9 is 15, and 15 plus 7 is 22. So it is 22 over 2, that is 11. We should all know that the semi-perimeter of triangle ABC equals to 11 units in its length. In the next step, we will find out this triangle ABC according to a special formula. Thereafter ABC, actually the special formula is good for any triangle. So thereafter ABC is equal to the square root of S times S minus A times S minus B times S minus C. S is the semi-perimeter of triangle ABC, that is 11. A, B, and C are the side lengths of triangle ABC. A equals to 6 units in its length, B equals to 9 units in its length, and C equals to 7 units in its length. A equals to 6, B equals to 9, C equals to 7. And the semi-perimeter S equals to 11. So the only thing that is left to do is to put the data inside this special formula for triangle ABC, and we find out the area of this triangle ABC. So according to this special formula, the area of our triangle ABC is equal to the square root of S. So perimeter S is 11 times S minus A. S is 11, A is 6, so S minus A is 11 minus 6, that is 5, times S minus B. S is 11, B is 9, so 11 minus 9 is 2. Times S minus C. S is 11, C is 7, S minus C is 11 minus 7, that is 4. So in total, we should find out that the area of our triangle ABC is equal to the square root of 11 times 5 times 2 times 4. The square root of 4 is 2, so we can take 4 from the root. So ABC equals to the square root of 4, that is 2. So inside the root we left only if 11 times 5 times 2. So the other ABC in total is equal to 2. Inside the root we have 15. Inside the root we left only with 11 times 5 times 2. And again, inside the root we left only with 11 times 5 times 2. It is 11 times 5 times 2. So it is 11 times 5. That is 55. And 55 times 2 is 110. And total, we found out that the area of triangle ABC, the area of our triangle ABC equals to 2 times square root of 110 square inch in size. The area of this triangle ABC equals to 2 times square root of 110 square inch in size. Actually, you know that any triangle that blocks a circle, like in our drawing, triangle ABC blocks the circle. We have a special formula for the area of a triangle that blocks a circle. This is triangle ABC that blocks this circle. According to the special formula, the area of triangle ABC that blocks this circle will be equal to the semi-perimeter of triangle ABC, that is S, and S is 11, times the radius of this circle that is described by triangle ABC. So the area of triangle ABC equals to the semi-perimeter of triangle ABC times the radius of the circle, the radius of this circle that blocks triangle ABC. We already found out that the area of triangle ABC equals to 2 times square root of 10, so and write down that the area of triangle ABC equals to 2 times square root of 110. It is equals to S, that is 11, times the radius of this circle that is described by triangle ABC, that is the missing variable. So in total, we found out that 2 times square root of 110 equals to 11 times R. Here we divide this equation by 11 and get that the radius R of this circle that is described by triangle ABC is equal to 2 times square root of 110 over 11. 2 times square root of 110 over 11 is equal to 1.907 units. So if you found out that the radius of this circle R that is described by triangle ABC is equal to 1.907 units in its length. We know that the sum of the angles in any quadrilateral is equal to 360 degrees. Repeat again, the sum of the angles in any quadrilateral is equal to 360 degrees. So in the drawing we have quadrilateral POLC. This is quadrilateral POLC. So the sum of the angles in this quadrilateral POLC is equal to 360 degrees. So which angles we have in quadrilateral POLC? 90 degrees plus 90 degrees is 180 degrees, plus theta plus the missing angle POL in total must be equal to 360 degrees according to the rule that I mentioned. So 180 degrees plus this is angle theta plus this is the missing angle POL. In total must be equal to 360 degrees according to the rule that I mentioned. Repeat again. The sum of the angles in quadrangle POLC must be equal to 360 degrees, that is to say 180 degrees, plus theta plus the missing angle POL in total must be equal to 360 degrees. Here we subtract 180 degrees from this equation. So 180 degrees will get cancelled here, and we're left only with theta plus the missing angle POL is equal to 360 degrees minus 180 degrees, it is 180 degrees. So in total we found out that theta plus the missing angle POL equals to 180 degrees. Here we subtract theta from this equation, and finally we get that the missing angle POL is equal to 180 degrees minus theta. So finally, this is the missing angle POL that is equal to 180 degrees minus theta. But we only found out that 180 degrees minus theta equals to 139.632 degrees. So this is an angle that equals to 180 degrees minus theta equals to 139. 0.632 degrees in its size. Our task is to find out the area of this green shape. So what is the area of the green shape? From the drawing, it is very easy to see that the area of the green shape total equals to the area of this quadrangle POLC minus the area of this sector POL. And again, the area of this green shape in total is equal to the area of quadrangle POLC minus the area of sector POL. The rounded line above POL is the sign for the sector. This means this sector POL. And again, the area of the green shape equals to the area of quadrangle POLC minus the area of this sector POL. In the next step, we will join points O and C together by a straight line. By joining points O and C, we actually divided quadrilateral PO and C into two parts. The first part, this is this right triangle POC or PC, and the second part is the other right triangle OLC. Therefore, it is very clear that the quadrilateral POLC must be equal to the sum of the earths of those two shapes that is consistent. Very simple. So the quadrilateral POLC equals to the of this right triangle POL plus the of this right triangle OLC. So write it down. Quadrilateral POLC equals to the of this right triangle POL plus the of this right triangle OLC. And again, I should remember that the area of quadrilateral POLC equals to the sum of the area of the two shapes that is consistent. That is to say, it equals to the area of the first shape that is triangle POL plus the area of the second shape that is triangle OLC. Minus the area of this sector POL. According to the formula that I presented to you a couple minutes ago, the area of this sector POL must be equal to the area of this circle that contains the sector, and the area of this circle is pi r squared. R is the radius of the circle, times the angle between the legs of the circle that is 139.632 degrees, over 360 degrees. And again, I should remember that the area of the sector POL, in total, it is equal to pi r squared. This is the area of this sector that contains the sector. R is the radius of the sector, times the angle between the legs of the sector that is 139.632 degrees over 360 degrees. What is the area of this right triangle POL? The area of right triangle equals to the base of the triangle times the height over 2. The base PO is R, the height PC is 5, and therefore in total the area of this right triangle POL is equal to 5R over 2. The area of the triangle POL equals to 5R over 2 square units in its size. Plus the area of the other right triangle OLC. The area of the OLC equals to the base that is OL that is R, the height LC is 5, so in total the area of the OLC equals to 5R over 2. The area of the OLC equals to 5R over 2 square units in its size. So in total the area of the green shape equals to 5R over 2 plus 5R over 2 minus the area of the sector POL that is pi r squared times 139.632 degrees over 360 degrees. We already found out that the radius R of this circle, the radius R, equals to 1.907 units in its length. So we solved the radius R by 9.107. We get that in total the area of sector POL equals to pi r squared, and pi r squared is pi times 1.907 squared times 139.632 degrees over 360 degrees. So in total, the area of sector POL equals to pi times 1097 squared times 139.632 degrees over 360 degrees. So we have this expression 5R over 2 plus 5R over 2. We take 2 as a common factor out of those two expressions. In the numerator we have 5r plus 5r is 10r, and 10r over 2 is 5r. So in total, value of this expression is 5r minus of the sector POL. Actually, pi times 907 squared times 139.632 degrees or 306 degrees. In total, the value of this expression is equal to 4.387 exponents in size. That is the sector POL. So in total, the green chap equals to 5r minus 4.37 minus 4.387. R is 1.907, therefore 5r is 5 times 107 is 5 times 1.907. That equals to 9.535 minus 4.387, 9.535 minus 4.387. In total, this equals to 5.14s coordinates inside. So if you follow the way of this green shape, it is equal to 5.148 coordinates inside. The way of the green shape in total equals to 5.148 coordinates inside. We finished with the first question. In the next step, I'll present you the second question, and we solve the second question by using 3 different methods. Our task in the second question is to find out the area of this square ABCD. So in the drawing we have square ABCD. This is diagonal DB of square ABCD. This is angle BDP. This is equals to 30 degrees in size. This is angle PBC. This is also equals to 30 degrees in size. This is line segment PB. This is equals to 5 units in its length. Again, our test is to find out the area of this square ABCD. So we'll start with the first method. We know that the diagonals of any square bisect the angles of a square. And again, the diagonals of any square bisect the angles of the square. Diagonal DB bisect angle ABC. ABC in total is 90 degrees. Diagonal DB bisect angle ABC. Therefore, this is the first half of angle ABC. It is equals to 45 degrees in its size. This is the second half. It is also equals to 45 degrees in size. this angle equals to 30 degrees, and therefore this angle must be equal to 15 degrees inside, because 15 plus 30 is 45 degrees. That is the size of the second half of angle ABC. Likewise, diagonal BD bisect angle ADC. Again, diagonal BD of square ABCD bisect angle ADC. So okay, this is the first half of angle ADC that equals to 45 degrees in its size. And this is the second half. It's also equals to 45 degrees in size. But this angle is 30 degrees, and therefore this angle also equal to 15 degrees in its size. Okay. In the next step, we will do a construction, that is to say, from the vertex C of square ABCD, we will draw angle bisector of this angle DCB. So this is an angle bisector. It bisects angle DCB into two halves. The first half is 45 degrees, and the second half is also 45 degrees. In the next step, we'll extend line 7 DP in such a way that we'll extend line 7 DP until it touches the angle bisector. And we will define the touching point of the extended line 7 DP with this angle bisector. This point is point Q. By doing this construction, we can do triangle DP DQC. This is triangle DQC. In triangle DQC, this angle equals to 45 degrees. This angle equals to 15 degrees. 45 degrees plus 15 degrees is 60 degrees. And therefore this third missing angle is equal to 120 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we will join points B and Q together by a straight line. By joining points B and Q together, triangle BQC. This is triangle BQC. So, in the next step, we'll prove that those two triangles can go into each other according to side angle side rule. Okay, again, we'll prove that triangle BQC can go into this triangle BPQ according to side angle side rule. So we have to prove that triangle BQC can go into this triangle BPQ according to side angle side rule. So what those two triangles can go into each other? First of all, side VC equals to side CD. They're both the sides of a square that are equal to each other. All the sides of a square are equal to each other. So side BC of triangle this triangle BQC equals to side DC of this triangle DQC. Okay, again, I should handle that side BC of triangle BQC equals to side DC of triangle BPQ. They're both the sides of a square, therefore they are equal to each other. Actually, we have to prove that those two triangles can go into each other. Okay? According to side against side rule. So we have to prove that triangle BQC can go into this triangle QDC. So actually side DC equals to side BC. In addition, we know that those triangles are both equal to 45 degrees and therefore they are equal to each other. So this is again BCQ triangle BQC. And it is equals to this angle, this is actually angle DCQ. Triangle DQC. And again, angle DCQ triangle BQC equals to angle DCQ and triangle BPQ. They are both equal to 45 degrees and therefore they are equal to each other. And this is triangle DQC. Suppose that those two triangles can go into each other according to side against side rule. So those two sides are equal to each other, those triangles are both equal to 45 degrees and therefore they are equal to each other. And finally, QC is the common side that belongs to both triangles. QC belongs to triangle QCB and QC of course belongs to triangle CQD. So QC is the common side that belongs to both triangles. Okay? Find out that QC equals to itself is a common side that belongs to both triangles. Okay, again, QC is a common side that belongs to both triangles. So can I know that QC equals to itself is a common side that belongs to both triangles. So I should prove that those two sides and the angle that is included between those two sides in this triangle BQC are corresponding equal to those two sides and the angle that is included between those two sides in this triangle BQC. And therefore those two triangles can go into each other according to side angle side rule. And again, those two sides and the angle that is included between those two sides in this triangle BQC are corresponding equal to those two sides. And the angle is included between those two sides in this triangle DCQ. And therefore those two triangles can go into each other according to side angle side rule. So if you don't, if you found out that triangle BQC convert, this is the sign of convert, so triangle DQC according to side angle side rule. And from the fact that those two triangles can go into each other, we will derive that P, that from the fact that those two triangles can go into each other, we will derive that those two corresponding angles must be equal to each other and their sizes. Okay. According to the rule that corresponding angles in congruent triangles are equal to each other. Those two triangles can go into each other, and therefore those two corresponding angles must be also equal to each other and their sizes. This is again QDC. In triangle DQC, and is equal to this angle, is a triangle QBC. In triangle BQC. Again, angle QDC angle QDC equals to angle in triangle QDC equals to angle QBC in triangle BQC. But we only found out that angle QDC equals to 15 degrees. We can argue that angle QDC equals to 15 degrees in its size. And from this equation, 15 equals to angle QDC equals to angle QBC. We derive that angle QBC is also equal to 15 degrees in size. Those two sides of the equation are equal to each other. So angle QBC equals to 15 degrees in its size. This is the missing angle QBC that is equal to 15 degrees in its size. Diagonal DB bisect angle ABC. The first half is 45 degrees, and this is the second half. It must be also equal to 45 degrees. So we have 15 degrees plus 15 degrees is 30 degrees, and therefore this missing angle must be equal to 15 degrees in its size, because the second half must be equal to 45 degrees in its size. So the missing angle is equal to 15 degrees in its size. So this is our triangle VQP. Here we will copy this right triangle DBP in a new page. This right triangle VDP. Copy it in a new page, and we'll implement rule 8 on this triangle BDP. Stephanie. This is triangle BDP, it is the point from the original drawing. Those two angles 15 degrees and 30 degrees in this missing angle, now all defined as an angles. This angle BPQ, it is defined as an exterior angle because it is located outside triangle BDP. The question is, what is the size of this exterior angle BPQ? What is the size of the exterior angle BPQ? So actually, Rule 8 answers on this question. Rule 8 will help us to find out the size of angle, the size of the exterior angle BPQ. So repeat quickly on Rule 8. Rule 8 is true in any triangle. This is triangle ABC that could be any triangle. Those are angles alpha, beta, and gamma that are defined as exterior angles. This is angle E. This is defined as an exterior angle because it is located outside triangle ABC. The size of this exterior angle, according to Rule 8, the exterior angle of a triangle is equal to the sum of the two interior angles that are not adjacent to it. So the size of this exterior angle E is equal to the sum of the two interior angles that are not adjacent to it. This is angle gamma that is definitely adjacent to angle E. The two other angles that are not adjacent to angle, the two other angles that are not adjacent to angle E are those two angles, alpha and beta. And according to this Rule 8, the size of the exterior angle E equals to the sum of the two angles that are not adjacent to it. The society is equal to alpha plus beta. So angle E equals to alpha plus beta. So this is the exterior angle BPQ. According to Rule 8, the size of the exterior angle BPQ equals to the sum of the two angles that are not adjacent to it. This is angle DPB that is definitely adjacent to angle BPQ. The two other angles that are not adjacent to angle BPQ are those two angles. According to Rule 8, the size of the exterior angle BPQ is equal to the sum of the two angles that are not adjacent to it. That are not adjacent to it. That is to say, it is equal to 15 plus 30. 15 degrees plus 30 degrees. So the size of the exterior angle BPQ according to Rule 8 is equal to 15 degrees plus 30 degrees, that is 45 degrees. In total, if you want to know the size of the exterior angle BPQ is equal to 45 degrees. According to Rule 8, of course. This is angle BPQ, this is equal to 45 degrees in its size. In triangle PBQ, this is triangle PBQ. 15 degrees plus 45 degrees is 60 degrees, and therefore this furnace area must be equal to 120 degrees in its size, according to the rule that the sum of the angles in the triangle is equal to 180 degrees. Likewise, in triangle BQC, 45 degrees plus 15 degrees is 60 degrees, and therefore this furnace area is equal to 120 degrees in size, according to the sum rule. In the next step, we will prove that those two triangles can go to each other according to angle, side, angle rule. Okay, again, for the triangle BCQ, this triangle can go into this triangle PQB according to angle, side, angle rule. So we have to form the triangle BQC, the lower triangle, can go to this triangle PQB according to angle, side, angle rule. So why those two triangles can go into each other? First of all, those two angles are both equal to 120 degrees and therefore they are equal to each other. So here this is angle BQC. And triangle BQC is equal to this angle, the angle PQB. And triangle BPQ. Okay, again, I should find out that angle BQC, triangle BQC equals to angle PQB, triangle PBQ. They are both equal to 120 degrees and therefore they are equal to each other. In addition, side QB is a common side that belongs to both triangles. Side QB is definitely belongs to triangle QBC. And side QB definitely belongs to triangle QPB. So QB is a common side that belongs to both triangles. QB equals to itself. And again, side QB is a common side that belongs to both triangles, so we can write down that QB equals to itself is a common side that belongs to both triangles. And finally, those two angles are both equal to 15 degrees and therefore they are equal to each other. So actually this is again QBC and triangle BCQ is equal to this angle, this is actually angle PBQ. And triangle PQB. And again, I should find out that angle QBC in triangle BQC equals to angle PBQ in triangle PQB. They are both equal to 15 degrees and therefore they are equal to each other. So I should find out that those two angles and the side that is included between those two angles, that is side QP, inside this triangle QCB are corresponding equal to those two angles, and the side that is included between those two angles, that is also side QB, in this triangle, triangle PQB. Therefore, those two triangles can go into each other according to angle, side, angle rule. Okay, again, those two angles and the side that is included between those two angles in triangle QBC are corresponding equal to those two angles, and the side that is included between those two angles in this triangle, triangle PQB. Therefore, those two triangles can go into each other according to angle, side, angle rule. Also found out that triangle QBC can win, this is the side can win, so triangle PQB according to angle, side, angle rule. And for the fact that those two triangles can go into each other, we realize that the corresponding sides are also equal to each other. That is to say, PB equals to BC. And again, PB PQB equals to side BC of triangle BQC. Why PB and BC are corresponding sides? Because PB is located, PB in triangle PQB is located in front of this angle is equal to 120 degrees in size. Likewise, side BC of triangle BQC is also located in front of this angle is equal to 120 degrees in size. So, according to the rule that corresponding angles can join triangles, so BP is the corresponding side of side BC. And according to the rule that corresponding sides and congruent triangles are equal to each other, again that those two triangles congruent to each other, and therefore those two corresponding sides, that is to say BP and BC, must be also equal to each other in their lengths. So PB equals to BC, but according to what is given in the equation, PB equals to 5. So you can write here that PB equals to 5, and from this equation 5 equals to BB, 5 equals to PB equals to BC, we derive that BC also equals to 5 units in its length. This is side BC, this is equals to 5 units in its length. Our task is to find out the area of this square ABCD. So what is the area of this square ABCD? Actually, we know that the area of any square equals to the length of one side squared. Therefore, the area of this square ABCD must equal to the length of one side squared. That is to say, it is BC squared. BC square. BC is 5, so BC square is 5 square. 5 square is 25. So in total, we found out that the area of square ABCD equals to 25 square units in size. And again, I found out already that the area of this square ABCD, that is the area that we're looking for in this question, is equal to 25 square units in its size. So we finish with the first method. In the next step, I'll present you how to find out the area of square ABCD according to the second method. So I repeat again that the diagonals of any square bisect the angles of the squares. Diagonal DB bisect angle ABC. So the first half is 45 degrees, this is the first half. It was 45 degrees in its size. This is the second half of angle ABC, that is also equals to 45 degrees in size. But this angle equals to 13, therefore the missing angle must be equal to 15 degrees in its size. So in this triangle BDP, 30 degrees plus 15 degrees is 45 degrees, and therefore this first missing angle must be equal to 135 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we will do a construction, that is to say, we will draw a circle around square ABCD in such a way that the vertex A of square ABCD will be the center of the circle that we will draw, and the diameter and the radius of the circle will be the sine length of square ABCD. That is to say, the radius of the circle will be equal to AB, and the radius of the circle will be also equal to AD. Okay, so we define the radius of the circle as x, so AB equals to x, the radius AD also equals to x. So this is the circle that we drew around square ABCD. I repeat again that point A is the center of the circle according to our construction, of course. AB is the radius of the circle, also according to our construction. AD is also the radius of the circle, according to our construction. The radius of the circle equals to x, according to our definition. So, AB is the radius of the circle that is equal to x units in its length, according to our construction. So, AB is the radius. A radius has two edges, and in any circle the first edge of any radius lie on the center of the circle, and the second edge lie on the circle itself. AB is also the radius, therefore AB, the first edge of AB lies on the center, and the second edge of the radius AB is B. B must lie on the circle because it is a radius, the radius of any circle. The edge of the radius of any circle must lie on the circle itself. Therefore, point B lie on the circle. That is to say, the circle passes for point B because AB is the radius, and the edge B of radius AB must lie on the circle. It is true for any triangle or for any radius. Okay, therefore it is true for this radius AB. So the circle passes for point B. Likewise, AD is the radius of the circle according to our construction. The radius of any circle has two edges. The first edge must lie in the center of the circle, that is point A. The second edge of radius AD must lie on the circle itself, so point D lie on the circle itself. So if you found out that the circle passes for point B and for point B, for point B and for point D. But again, if you found out that the circle that we drew passes for points B and D, because they are both AB and AD, they are both the radius of the circle, and therefore the radius of any circle, the second edge of the radius of any circle lie on the circle itself. Very simple. Okay. So here we can implement rule 13, but first of all we know that the sum of the angles around any point is equal to 360 degrees. So the sum of the angles around point A must be equal to 360 degrees. Which angles we have around point A? We have this angle that is 90 degrees because it is an angle of a square, plus the missing angle must be equal to 360 degrees according to the rule that I mentioned. Therefore, this missing angle must be equal to 270 degrees in its size. 270 degrees plus 90 degrees is 360 degrees. That is the sum of the angles around any point. So this is center angle DAB that is equal to 270 degrees in size. This angle DBP equals to 135 degrees in size. 270 degrees over 2 is 135 degrees. So center angle DAB is twice as large of angle DBP. Again, center angle DAB is equal to 270 degrees. It is twice as large of this angle DBP. So you can implement rule 13. According to rule 13, the center angle is twice as large as the peripheral angle subtended on the same chord. In the drawing, we have a circle. This is peripheral angle ACB. is equals to theta degrees in size. And subtend on chord AB. Likewise, this is center angle AOB. It is also subtend on the same chord AB. And because of the fact that the peripheral angle and the center angle are both subtend on the same chord AB, the size of the center angle must be twice as large as the size of the peripheral angle. The size of the peripheral angle is theta, and therefore the size of the center angle must be equal to 2 theta. So we can actually implement all 13 in our drawing. So we'll put in our drawing, we have, this is center angle DAB, this is equal to 270 degrees in its size. It's subtend on chord DB. Likewise, this is again DPB. This is equals to 135 degrees inside, and it's subtend on the same chord DB. So, angle DPP obeys to all 13. Why? Because the center angle DAB, it's subtend on DB, is twice as large as angle DBP, that is also subtend on the same chord DB. Again, angle DBP equals to 135 degrees. Center angle DB equals to 135 degrees times 2, that is 270 degrees. And because of the fact that angle DPB obeys to all 15, and to all 13, it must be a peripheral angle. Okay? And again, because of the fact that angle DPB obeys to all 13, it must be a peripheral angle. So, angle DPB is a peripheral angle. We know that all the 3 vertices of any peripheral angle lie on the circle. The peripheral angle DBP has 3 vertices, D, P, and B. Point D lie on the circle itself, point B lie on the circle itself, and therefore point P must lie on the circle itself. Okay? Because it is a peripheral angle. So if you found out that the circle passes for point P, and the circle passes for point P, according to all 13. Okay? So, point A is the center of the circle, point P is the point on the circle itself, so point P is the radius of the circle, is equals to x units in itself according to our definition. So here we have, this is triangle ABP. Triangle ABP, angle ABP equals to 45 degrees plus 15 degrees, that is 60 degrees. So in the next step, I'll copy triangle ABP in a new page, and we analyze this triangle ABP. But again, we're talking about triangle APB. This is again ABP, this is equals to 15 degrees plus 45 degrees is 60 degrees. We're talking about this triangle ABP. But again, angle ABP equals to 45 degrees plus 15 degrees, that is 60 degrees. Actually, this is triangle ABP, the point from the original drawing. Angle ABP equals to 60 degrees in size. Those two sides are both equal to x and therefore they are equal to each other. We have the rule that in front of equal sides in the triangle there are equal angles. So in front of those two equal sides, we have those two angles that must be also equal to each other and their sizes. But this angle equals to 60 degrees and therefore this angle must be equal to 60 degrees in size. $60 plus 60 degrees is 120 degrees, and therefore this furnace angle must be equal to 60 degrees in its size, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. So all the angles of triangle ABP, they are all equal to 60 degrees in their sizes, and therefore it is an equilateral triangle. You know, triangle ABP is an equilateral triangle. We know that all the sides of any equilateral triangle are equal to each other. Let us say BP equals to BA equals to AP. So BP equals to AB. According to what is given as the question, BP equals to 5. So we can write that BP equals to 5. And from this equation, 5 equals to BP equals to AB, we have that AB equals to 5. Those two sides of the equation are equal to each other. So AB equals to 5. Our task is to find out the of this first square ABCD. So this is the square ABCD. Actually, we know that the of any square equals to the length of one side squared. So it is AB squared. AB squared. AB is 5, therefore it is 5 squared, it is 25. So now if you want to know that the of square ABCD is equals to 25 squared in its size, according to the second method. So we finish with the second method. The next step, I present to you how to find out the of the square ABCD according to the third method. In the third method, we define the length of side AB as x. Likewise, we define the length of side AD as x. Repeat again, DB, diagonal DB bisect angle ABC. The first half equals to 45 degrees in size. This is the second half of angle ABC that is also equal to 45 degrees in its size. So 30 degrees plus the missing angle is 45 degrees. Therefore the missing angle must be equal to 15 degrees in its size. So in triangle BDP, 15 degrees plus 30 degrees is 45 degrees, and therefore this third missing angle must be equal to 155 degrees in its size. According to the rule that the sum of the angles in any triangle is equal to 180 degrees. In the next step, we'll implement the Pythagoras theorem. This is of course a right angle because it is a square. ABCD is a square. In the next step, we'll implement the Pythagoras theorem on this triangle BAD. According to the Pythagoras OM in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in triangle ABD, here by PT is a version for what I was doing. So in triangle ABD, it means that BD squared, that is the square of the hypotenuse, equals to AD square plus AB square. BD, the hypotenuse BD is the missing side, so it is. So it is BD square equals to AD square. AD is x, so AD square is x square plus AB square. AB is also x, so AB square is x square. So in total, you should know that BD square equals to x square plus x square. X square is 2x square. So BD square equals to 2x square. Here we take a root out of this equation and finally get that the hypotenuse BD is equal to the square root of 2 times the square root of x squared. The square root of x squared is x. So in total, you should know that the length of the hypotenuse BD is equal to the square root of 2 times x units in its length. The next time we focus on triangle BDP. And we will implement the law of sines in this triangle BDP. And pretty quickly on the law of sines. The law of sines is true in any triangle. This is triangle ABC that could be any triangle. Side AB of triangle ABC equals to C units in its length. Side AC of triangle ABC equals to B units in its length. Side BC equals to A units in its length. This is angle BAC, that is equals to capital A degrees inside. This is angle ABC, that is equals to capital B degrees inside. This is angle ACB, that is equals to capital C degrees inside. This triangle ABC that could be any triangle, according to the law of sines, the following equation is true. That A over sinus A equals to B over sinus B equals to C over sinus C. Again, this triangle ABC, according to the law of sines, A over sinus A equals to B over sinus B equals to C over sinus C. You can implement the law of sines in triangle DPB. According to the law of sines in triangle DPB, dB over 135 degrees, dB over sinus 135 degrees, equals to BP over sinus 30 degrees. And again, in triangle DPB, according to the law of sines, you get that dB over sinus 135 degrees equals to BP over sinus 30 degrees. BP equals to 5, so it will be BP by 5. So BP is 5 over sinus 30 degrees. Sinus 30 degrees is 1 hour. This equals to dB. dB equals to the square root of 2 times x units in its length. a sinus 135 degrees. Sinus 135 degrees equals to the square root of 2 over 2. So total, if you found out that 2x over square root of 2 over 2 equals to 5 over 1 half. Here we move 2 to the numerator and square root of 2 to the denominator, and get that the total value of this expression will be equal to the square root of 2 times x times 2 over square root of 2. And is equals to 5 over 1 half. 5 over 1 half is 10. So total, if you found out the square root of 2 times x times 2 over square root of 2 equals to 10. Here we have square root of 2 in the numerator, square root of 2 in the denominator, so square root of 2 will get cancelled. So left in this side of the equation only with 2x equals to 10. 2x equals to 10. Here we divide this equation by 2 and finally get that x equals to 10 over 2, that is 5. So AB is equals to x, AB equals to x, and x equals to 5. So the length of one side of square ABCD equals to 5 units inside. Now let's just find out the of this square ABCD. The of square ABCD equal to the length of one side, that is x squared. The length of one side x is 5, so x squared is 5 squared. 5 squared is 25. So total, if you want to do the of square ABCD according to the first method, is equal to 25 square units inside. So here, in all the three methods, we actually found out that this square ABCD is equal to 25 square units inside. So we finish with the third method. In the next step of some of the lecture, we start with the first question, of course. Our task in the first question is to find out the area of this ring shape. So in the drawing, we have a circle that is described by triangle ABC. We know that side AB of triangle ABC equals to 6 units in itself, side AC equals to 7 units in itself, side BC equals to 9 units in itself. Again, our task is to find out the area of this ring shape. So first of all, we define the size of angle ACB. This angle is theta, and we represent the law of cosines this triangle ABC. According to the law of cosines, the law of cosines is true in any triangle. This is triangle ABC that could be any triangle. Side AB of triangle ABC equals to A units in itself, side AC equals to B units in itself, side BC equals to C units in itself. This is again BAC that is equals to theta degree in size. Again, according to this law, the law of cosines, this triangle ABC that could be any triangle, the following equation is 2. That cosine theta equals to h squared plus b squared minus c squared over 2 times a times v. Again, cosine theta equals to h squared plus b squared minus c squared over 2 times a times v. Okay, implemented all the law of cosines in this triangle ABC. According to the law of cosines, in this triangle ABC, cosine theta equals to ac squared plus cb squared minus AB squared over 2 times AC times CB. Okay, again, according to the law of cosines, is this triangle ABC, the following equation is 2. That cosine theta equals to AC squared plus BC squared minus AB squared over 2 times AC times CB. So this equation is the implementation of the law of cosines in our triangle ABC. So cosine theta equals to AC squared. AC is 7, therefore AC squared is 7 squared. AC squared is 7 squared. Plus CB squared. CB is 9, therefore CB squared is 9 squared. Minus AB squared. AB is 6, therefore AB squared is 6 squared. Over 2 times AC times AB. AC is 7. CB is 9, so it is 2 times 7 times 9. So the denominator over 2 times 7 times 9, it is 2AB. So cosine theta equals to 7 squared. 7 squared is 49, plus 9 squared, that is 81. 6 squared is 36, over 2 times 7 times 9. 7 times 9 is 63, 63 times 2 is 126. So in total we have found out that cosine theta equals to 49, plus 81 on 36 over 126. So cosine theta equals to 49 plus 81 is 130 on 36. It is 130 on 36 over 226. 130 on 36 is 94 over 226. So in total cosine theta equals to 94 over 126. 94 over 126 is 0.7169. So cosine theta in total equals to 0.7169. Again, cosine theta equals to 0.7169. I would like to find out the value of angle theta itself, the size of angle theta itself. In order to find out the size of angle theta, we operate the opposite function of cosine, that is r cosine, on the result of cosine theta, that is 0.7169. This way we get angle theta itself. So r cosine of the result of cosine theta, that is 0.7169, it is equals to angle theta itself. R cosine of 0.7169 is equals to 40 degrees, 0.38, 40 degrees, 0.638 degrees in its size. So total we found out that angle theta equals to 40 degrees, 0.368 degrees in its size. Therefore 180 degrees equals to 180 degrees on theta equals to 180 degrees minus 40.368, that is 139.632 degrees in its size. Okay, again 180 degrees on theta equals to 139.632 degrees. In the next step, we define the center of this angle, this point is point O. We define the radius of this angle as R. We define the point of tendency of tangent BC with this angle, this point is point L. We define the point of tendency of tangent AB with this angle, this point is point Q. And we define the point of tendency of tangent AC with this angle, this point is point P. In the next step, we join points O and L together by a straight line. Point O is the center of the angle, point L is the point of the second step, therefore O is the radius of the angle, that is equals to R. So here we can implement all one, because the radius of L is equals to R, the radius of L is drawn to point L, that is the point of tendency of tangent BC 50 seconds. Now you order that is drawn to the point of tendency, then tangent BC will be perpendicular to the LO. If BC is perpendicular to LO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule 1. Likewise, the joint points are repeated with the western line. OP is, of course, the radius of the second is equal to R. Point P is the point of tendency of tangent AC 50 seconds. So, according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. In the next step, implemented, first of all, we define line segment BL as A. Line segment BL equals to minus in its length. Then we implemented rule 2 in our drawing. Okay, click on rule 2, according to rule 2. The lengths of two tangents from a common standpoint per second are equal. So in the drawing, we have a second, this is the common standpoint point P. From this common standpoint point P, we have two tangents to the second, tangent PA and tangent PB. According to this rule, they are equal to each other. According to this rule 2, they are equal to each other. That is to say, PA equals to PB. So we can implement rule 2 in our drawing. When put in our drawing, we focus on this common standpoint point B. From this common standpoint point B, we have two tangents to the second, tangent BL and tangent BQ. According to rule 2, they are equal to each other. That is to say, BL equals to BQ. Well, BQ is A, therefore BL is A, therefore BQ must be also equal to A units in its length. According to rule 2. So BQ equals to A, BA equals to 6, and therefore in total AQ equals to BA that is 6 minus BQ that is 8. So in total AQ equals to 6 minus 8. Likewise, only the length of line LC, LC equals in total to BC that is 9 minus BL that is 8. So in total LC equals to 9 minus 8. So in the next step we implemented rule 2, this common standpoint point A. From the common standpoint point A, we have two tangents to the second, tangent AQ and tangent AP. And according to rule 2, they are equal to each other. That is to say, AQ equals to AP. But AQ is 6 minus 8, therefore AP must be equal to 6 minus 8 according to rule 2. In the next step, we implemented rule 2 on this common standpoint point C. From the common standpoint point C, we have two tangents to the second, tangent CL and tangent CS, tangent CL and tangent CP. And according to rule 2, they are equal to each other. That is to say, CL equals to CP. But CL equals to 9 minus 8, therefore CP must be also equal to 9 minus 8 in itself, according to rule 2. AC, side AC of triangle ABC equals to 7 units in its length, according to what is given in the question. Side AC consists of two line segments, line segment AB and line segment PC. Therefore, AC in total must equal to AP plus PC. AC equals to AP plus PC. So AC equals to AP that is 6 minus 8 plus PC that is 9 minus 8. So in total AC equals to 6 minus 8 plus 9 minus 8. 6 plus 9 is 15 and 1 same minus 8 minus 2 8. So in total AC equals to 15 minus 2 8. AC is 7, so substitute AC by 7, so 7 equals to 15 minus 8. Here we add the 2a and subtract the 7 from this equation simultaneously. And finally found out that 2a equals to 15 minus 7 is 8. So 2a equals to 8. Here we divided the equation by 2 and finally found out that a equals to 8 over 4, 8 over 2, that is 4. So a equals to 4 units in itself. Here it equals to a equals to 4 units in itself. That's the VQ or tangent VQ that equals to 8 equals to 4 units in itself. QA equals to, AQ equals to 6 minus 8, that is 6 minus 4 is 2. Likewise, AP equals to 6 minus 8, it is 2. PC equals to 9 minus 8. 9 minus 8 is 9 minus 4, that is 5. Likewise here, LC equals to 9 minus 8, that is 5. So in the next step, we calculated the semi-perimeter of this triangle ABC. the semi-perimeter of any triangle equals to the perimeter over 2. And the perimeter of any triangle is the sum of the three side lengths of the triangle. In this case, it is AB plus BC plus AC. So the perimeter and the semi-perimeter of triangle ABC equals to the perimeter that is AB plus BC plus AC is actually 6 plus 9 plus 7 divided by 2. 6 plus 9 is 15, 15 plus 7 is 22, so it is 22 over 2, that is 11. So the semi-perimeter of this triangle ABC equals to 11 units in its length. In the next step, I presented to you a special formula for finding out the area of any triangle. So the area of any triangle is equal to the square root of S times S minus A times S minus B times S minus C. A, B, and C are the side lengths of the triangle. S is the semi-perimeter of the triangle. In our case, the semi-perimeter S equals to 11. The length of side AB is equals to A is 6. The length of side BC is equals to 9. B equals to 9. The length of side AC, that is defined as C, is 7. So C equals to 7. Semi-perimeter is 11. So the area of triangle ABC equals to the square root of S is 11 times S minus A. S is 11, A is 6, so therefore S minus A is 11 minus 6, that is 5, times S minus B. S is 11, B is 9, so 11 minus 9, that is 2, times S minus C. S is 11, C is 7, so 11 minus 7 is 4. So in total, we found out that the area of triangle ABC is equal to the square root of 11 times 5 times 2 times 4. We took 4 out of this root. The square root of 4 is 2. So we took 4 out of this root. So we found out that the area of triangle ABC equals to 2 times the square root of 11 times 5 times 2. That is what is left after we took 4 out of the root. So the area of triangle ABC in total equals to 2 times the square root inside the root. We have 11 times 5 is 55. 55 times 2 is 110. So in total the area of triangle ABC equals to 2 times the square root of 110 surroundings inside. The area of this triangle ABC equals to 2 times square root of 110 surroundings inside. Actually, we have a special formula for the area of any triangle that blocks a circle. Again, we have a special formula for the area of any triangle that blocks a circle. This is triangle ABC that blocks this circle. Therefore, the area of this triangle ABC will be equal to the semi-perimeter S of the triangle ABC, that is 11, times the radius of the circle that is described by triangle ABC. And again, the area of triangle ABC equals to the semi-perimeter of the triangle ABC times the radius of the circle that is blocked by triangle ABC. It is described by triangle ABC. We already found out that the area of triangle ABC equals to 2 times square root of 10. So it's inside. S is 11, R is the missing variable. So we found out that 2 times square root of 110 equals to 11 times R. Here we divided this equation by 11 and found out that the radius of this circle, the radius R of this circle that is described by triangle ABC equals to 2 times square root of 10 over 11. 2 times square root of 10 over 11 is 9.07 units. So the radius of this circle R equals to 1.907 units in its length. In the next step, I presented to you the notion of a sector. What is a sector? A sector is a portion of a circle. You can see sector POL is a portion of this circle enclosed by 2 radii and arc LP between them. And again, the green shape A or B is a sector. It is like a slice of a pizza. Sector A or B is enclosed by those two radii and RKB between them. The two radii are defined as the legs of the sector. So angle theta is located between the legs of the sector, and the area of the sector A or B equals to pi r squared, that is the area of the circle that contains the sector, times the angle between the legs of the sector that is theta over 360 degrees. Okay, again, the area of sector A or B. Here the rounded line above A or B is the same for a sector. The area of sector A or B equals to pi r squared times theta over 360 degrees. Our task is to find out the area of this green shape. What is the area of this green shape? For the drawing, it is very easy to see that the area of this green shape in total equals to the area of quadrangle POLC minus the area of this sector POL. Okay, then the area of this green shape equals to the area of this quadrangle POLC minus the area of this sector POL. Again, the area of the green shape in total equals to the area of quadrangle POLC minus the area of sector POL. In the next step, we join points O and C together by straight line. By joining points O and C, we divided quadrangle POLC into two parts. It is very clear and ready to say that the area of sector POL, the area of quadrangle POLC must be equal to the sum of the areas of those two shapes that it consists of. That is to say, the area of quadrangle POLC in total equals to the area of this right triangle POC minus plus the area of this right triangle OLC. Okay, again, the area of quadrangle POLC must be equal to the sum of the areas of those two shapes that it consists of. That is to say, it equals to the area of this right triangle POC plus the area of this right triangle OLC. And again, the area of sector, the area of quadrangle POLC in total must be equal to the sum of the areas of the two shapes that it consists of. That is to say, it must be equal to the area of the first shape, that is the area of the right triangle POL, plus the area of the second shape that it consists of, that is the area of the right triangle OLC, minus the area of the sector POL. According to the formula that I presented to you a couple of minutes ago, the area of this sector POL must be equal to pi r squared, that is the area of this circle that contains the sector, times the angle between the legs of the sector, that is 139.632 degrees over 360 degrees. So if you found out that the area of sector POL equals to pi r squared times the angle between the legs of the sector, that is 139.632 degrees over 360 degrees. The area of a triangle equals to the base of the triangle times the height over 2. So the area of the right triangle OPC equals to the base PO, that is R, times the height PC, that is 5 over 2. So in total, the area of this right triangle OPC equals to 5R over 2. The area of BO equals to 5R over 2. Plus the area of this right triangle OLC. The area of this right triangle OLC equals to the base OL, that is R, times the height LC, that is 5 over 2. So the area of the right triangle OLC also equals to 5R over 2 square in size. Minus the area of sector POL is equals to pi r squared times 139.632 over 360 degrees. R, the radius R of the circle equals to 1.907 units in its length. So we substitute R in this equation by 9.107. So R squared equals to 1.907 squared. So pi r squared is pi times 1.907 squared times 139.632 over 360 degrees. 5R over 2 plus 5R over 2 is 5R. In total, the value of this expression equals to 4.387 square in size. R is 1.907, therefore 5R is 5 times 1.107, that is 9.535 minus 4.387 is equals to 5.148 square inside. So in total, if you order the derivative that you're looking for this question, it is derivative of this ratio equals to 5.148 square inside. We finish with the first question. In the next step, I'll present to you, I'll repeat on the solution of the second question in 3 different methods. Our task in the second question is to find out the of this square ABCD. And the moment we have square ABCD, this is diagonal DB of square ABCD. This is again BP, BDP, this equals to 30 degrees in size. This is again QBC, this is also equals to 30 degrees in size. This is again PBC, this is also equals to 30 degrees in size. This is line segment PB, this is equals to 5 units in its length. Again, our task is to find out the of this big square ABCD. So first of all, we'll start with the first method, of course. We know that the diagonals of any square bisect the angle of the square. Again, the diagonals of any square bisect the angles of the square. Diagonal BD bisect the angle ABC. The first half is 45, and the second half is the first half is 45 degrees, and this is the second half, this is 45 degrees also. But this angle equals to 30 degrees, and therefore this angle must be equal to 15 degrees in size. Likewise, diagonal DB bisect the angle ABC. The first half, this is the first half, that is 45 degrees. This is the second half, this is also 45 degrees. But this angle equals to 30 degrees, and therefore this angle must be equal to 15 degrees in size. So, in the next step, we did a construction, that is to say, from point C, we draw angle bisector of angle DCB. And again, from the vertex C of square ABCD, we draw angle bisector of this angle DCB. So it is an angle bisector. So the first half is 45 degrees, and the second half is also 45 degrees. In the next step, we extended line 7DP inside, until it touches the angle bisector. We define the touching point of the extended side DP of the angle bisector. This point is point Q. By doing this construction, we created triangle DQC. In triangle DQC, 45 degrees plus 15 degrees is 60 degrees, and therefore this first angle must be equal to 120 degrees inside, according to the rule that the sum of the angles in any triangle is equal to 180 degrees. The next step, we join points B and Q together by straight line. We join points B and Q together, triangle BQC. So in the next step, we prove that triangle BQC, this is triangle BQC, is congruent to this triangle DQC. Prove that those two triangles congruent to each other according to side angle side rule. So why those two triangles congruent to each other? First of all, those two sides are both the sides of a square, therefore they are equal to each other. We know that the sides all the sides of any square are equal to each other. So those two sides are equal to each other. In addition, those triangles are both equal to 45 degrees, therefore they are equal to each other. And finally, side CQ is a common side that belongs to both triangles, so we can write out that the CQ equals to itself as a common side that belongs to both triangles. So we found out that those two sides and the angle that is included between those two sides in this triangle BQC are corresponding equal to those two sides and the angle that is included between those two sides in this triangle DQC. Therefore, those two triangles can go to each other according to side angle side one. And again, if you remember that triangle DQC can go to triangle DQC according to side angle side one. And from the fact that those two triangles can go into each other, we learn that those triangles must be also equal to each other in their sizes. According to the rule that corresponding angles in congruent triangles are equal to each other, those two triangles can go into each other, and therefore those two corresponding angles must be also equal to each other in their sizes. So if you found out that this is again QDC, angle QDC, triangle QDC equals to angle QBC, triangle BQC. But we already found out that angle QDC equals to 15, so we can write here that angle QDC equals to 15, and from this equation 15 equals to angle QDC equals to angle QBC, we derive that 15 degrees equals to angle QBC. Those two sides of the equation are equal to each other. So QBC equals to 15 degrees in size. This is angle QBC, this equals to 15 degrees in its size. Diagonal DB bisects angle ABC. The first half is 45 degrees. This is the second half. This must be also equal to 45 degrees. So 15 degrees plus 15 degrees is 30 degrees, and therefore this first missing angle must be equal to 15 degrees in size, because 15 times 3 is 45 degrees. That is the size of this second half of angle ABC. So this angle must be equal to 15 degrees in its size. So, in the next step, I presented to you rule 8, and we presented rule 8 in this triangle BDP. So, actually I copied triangle BDP in a page and implemented rule 8 in this triangle BDP. This is triangle BDP that I copied from the original drawing. Those triangles that are located inside ABC defined as triangles. This is external BPQ, it is external because it is located outside the triangle. The question is, what is the size of the external BPQ? Actually, rule 8 answers on this question. Okay, according to rule 8, the external of a triangle is equal to the sum of the two triangles that are not adjacent to it. This is triangle ABC that could be in a triangle. Those triangles alpha and beta and gamma are defined as triangles. This is angle E, angle ECB, ECF equals to 80 degrees in size, is defined as an external. What is the size of this external? E? It is equal, according to this rule, it is equal to the sum of the two triangles that are not adjacent to it. This is an angle gamma that is definitely adjacent to angle E. The two angles that are not adjacent to angle E are those two angles alpha and beta. Therefore, according to this rule 8, the size of angle E is equal to the sum of those two triangles that are not adjacent to this angle E. That is to say, it is equal to alpha plus beta. So in conclusion, if you found out that angle E equals to alpha plus beta, that is actually the sum of the two angles that are not adjacent to it. E equals to alpha plus beta. So in the next step, actually implemented all 8 in our drawing. According to all 8, we got the answer on the question about the size of this hexagon BPQ. The size of this hexagon BPQ equals to the sum of the two angles that are not adjacent to it. This is angle DPB, this is definitely adjacent to angle PBQ. Those are the two angles that are not adjacent to it. That is to say, the size of the hexagon BPQ equals to 15 plus 30 degrees. Hexagon BPQ equals to 15 plus 30 degrees, that is 45 degrees. The hexagon BPQ equals to 45 degrees in its size, according to all 8. This is angle BPQ, that is equals to 45 degrees in its size. So it's angle PBQ. 45 degrees plus 15 degrees is 60 degrees, and therefore this third here must be equal to 120 degrees in its size, according to the rule that the sum of the angles in an angle is equal to 180 degrees. In the next step, we focus on this triangle BQP. This triangle BQP. 15 degrees plus 45 degrees is 60 degrees, and therefore this missing must be equal to 120 degrees inside, according to the sum rule. Okay. In the next step, we prove that those two triangles can go into each other according to angle side angle rule. That is to say, triangle BPQ can go into this triangle BQC according to angle side angle rule. So why those two triangles can go into each other? First of all, those two angles are both equal to 120 degrees, and therefore they are equal to each other. In addition, BQ is the common side that belongs to both triangles, so we can write down that BQ equals to itself as the common side that belongs to both triangles. And finally, those two angles are both equal to 15 degrees, and therefore they are equal to each other. So we should find out that those two angles and the side that is included between those two angles, that is side QB, triangle BQC, corresponding equal to those two angles, and the side that is included between those two angles, that is also side BQ, in this triangle BQB. And therefore, those two triangles can go into each other according to angle side angle rule. And again, I should find out that triangle QBP can go into triangle PQB according to angle side angle rule. And from the fact that those two triangles can go into each other, we learn that the corresponding sides are equal to each other. PB is the corresponding side of BC. PB in triangle PQB is the corresponding side of side BC in triangle BQC. Why? Because PB in triangle PQB is located in front. The angle is equal to 120 degrees. Likewise, in triangle BQC, BC is located in front of this angle is equal to 120 degrees. And therefore, EP is the corresponding side of BC. According to the rule, the corresponding sides and congruent triangles are equal to each other. Again, that those two triangles can go into each other, and therefore those two corresponding sides, BP and BC, must be also equal to each other on the left. So PB equals to BC. I don't know that PB equals to BC, but according to what is given in the question, PB equals to 5. So we can write that PB equals to 5. PB equals to 5, and on this equation 5 equals to PB equals to BC, we know that BC also equals to 5. Those two sides of the equation are equal to each other, so BC equals to 5. One side of square ABCD, BC equals to 5. And we know that the opposite square equals to the length of one side squared. So the of square ABCD equals to the length of one side, that is BC squared. BC is 5, so BC squared is 5 squared, that is 25. So I don't know if you found out that the of this square ABCD is equals to 25 squares in its size. We finish with the first method. In the next step, I'll repeat on the solution of the second method and find out the of the square ABCD according to the second method. Diagonal DB bisect the angles of the square. Diagonal DB bisect angle ABC. This is the first half of angle ABC, that is 45 degrees. This is the second half, it is also 45 degrees. But this angle equals to 30 degrees, and therefore this piece angle must be equal to 15 degrees in size. Okay. So 15 degrees plus 30 degrees is 45 degrees. Therefore, this angle must be equal to 135 degrees in size, according to the rule that I mentioned too much times, that the sum of the angles in the triangle is equal to 180 degrees. So, in the next step, we did a construction. That is to say, we draw a circle around this square ABCD in such a way that point A will be the center of the circle, and the side length of square ABCD will be the radius of the circle. So we define side AB is x, so side AD also equals to x. The radius of the circle that we will construct. So this is the circle that we draw around square ABCD. As I mentioned before, we draw a circle in such a way that point A, vertex A of square ABCD equals to vertex A is the center of the circle that we built, and we built the circle in such a way that AB is the radius of the circle, AD is also the radius of the circle that we define as x. So AB is the radius of the circle. The radius of any circle has two edges. The first edge A must lie on the center of the circle. The second edge of the radius AB, that is B, must lie on the circle itself. All the radius of any circle, there are two edges. The first edge of the radius must lie on the center of the circle, and the second edge must lie on the circle itself. That is to say, the second edge B of the radius AB is located on the circle itself, because it is a radius. Okay? The edge of the radius of any circle must lie on the circle itself. Therefore, point B is definitely lying on this circle. Therefore, the circle passes for point B. Likewise, the radius AD has two edges. The first edge of the radius AB on the radius AD lie on the center of the circle. The second edge is D. The second edge of any radius must lie on the circle itself. Therefore, point D, that is the second edge of the radius AD, must lie on the circle itself. So I shall found out that those 2 points B and D, they both lie on the circle itself. Therefore, the circle must pass from point B and D. Because those are the radius of the circle. The edge of the radius of any circle must lie on the circle itself. So, point B and D are located on the circle itself. So, we know that the sum of the angles around any point is equal to 360 degrees. Again, the sum of the angles around any point is equal to 360 degrees. This is square ABCD, so therefore this angle equals to 90 degrees. So plus this missing angle, in total must be equal to 360 degrees according to the rule that I mentioned. Therefore, this missing angle must be equal to 270 degrees in size. 270 degrees plus 90 degrees, it is 360 degrees. That is the sum of the angles around any point. Okay, so Actually, this is center angle DAB. Center angle DAB is equal to 270 degrees in its size and its subset on chord DB. Again, center angle DAB equals to 270 degrees in its size and its subset on this chord called DB. Likewise, we have angle DPB. We only found out that angle DPB equals to 135 degrees in its size. This is angle DPB that's subset on the same chord called DB. And it equals to 135 degrees in its size. 270 degrees over 2 is 135 degrees. That is to say, center angle DAB is twice as large as angle DBP. Again, center angle DAB is equals to 270 degrees, it's twice as large of angle DPB. So here we can implement rule 13. A bit quickly on rule 13. A center angle is twice as large as the peripheral angle subtended on the same chord. In the drawing, we have a circle. This is peripheral angle ACB. This is equal to theta degrees in its size and is subtended on chord AB. Likewise, this is center angle AOB. That is also subtended on the same chord AB. So those two angles, they are both subtended on the same chord AB. And according to this rule, rule 13, the size of the center angle EOB must be twice as large of the size of this peripheral angle ACB that's subtended on the same chord AB. The size of center angle ACB is theta, and therefore the size of this peripheral angle ACB equals to theta, and therefore the size of this center angle AOB that is subtended on the same chord AB must be equal to 2 theta. So we can actually implement rule 13 in our drawing. Why? Because in our drawing we have center angle DAB is equal to 270 degrees in its size and it's subtended on chord DB. Likewise, we have angle DPB. It is also subtended on the same chord DB. You can see that angle DPB is subtended on chord DB. So those two angles, they are both subtended on the same chord DB. Center angle DAB is twice as large as angle DPB. This is 135 degrees. 135 degrees times 2 is 270 degrees. So center angle DAB is twice as large as this angle DPP. And therefore, angle DPP obeys to rule 13. Why? Because those two angles are both subset on the same chord DB, and the size of this angle is half of the size of this angle. Again, center angle DAB is twice as large as this angle. 125 degrees times 2 is 270 degrees. So, if those two angles, they are both lie on the same chord DB, and the size of the center angle is twice as large the size of this angle, that is 135 degrees. So actually, we found out that angle DBP obeys to rule 13, and therefore angle DBB must be a peripheral angle, because it obeys to rule 13. We know that the vertices, all the three vertices of any peripheral angle lie on the circle itself. Point D lie on the circle, point B lie on the circle, and point P must lie on the circle itself, of course. That is to say, if we found out that point P lie on the circle, because DPP is a peripheral angle, and all the three vertices of any peripheral angle must lie on the circle itself. So point P lie on the circle itself, therefore this circle passes for point P. Okay? So point A is the center of the circle, point P is the point of the circle itself, therefore AP is the radius of the circle, is equals to X according to our definition. In the next step, we focus on this triangle APB. And again, we focus on this triangle ABP. This triangle ABP angle ABP equals to 45 degrees plus 15 degrees, that is 60 degrees. So angle ABP equals to 60 degrees in size. In the next step, I copied triangle ABP in a new page and analyze this triangle ABP. Actually, this is triangle ABP that I copied from the original drawing. We already found out that angle ABP, this is angle ABP, this is equals to 60 degrees in size. In front of those two equal sides, we have those two angles that must be also equal to each other in their sizes, but this angle equals to 60 degrees, and therefore this angle must be also equal to 60 degrees in size. 60 degrees plus 60 degrees is 120 degrees, so this first angle must be equal to 60 degrees in size according to the rule that the sum of the angles in a triangle is equal to 180 degrees. So all the three angles inside the angle, inside triangle ABP are equal to 60 degrees in their sizes. Therefore, triangle ABP is an equilateral triangle. Triangle ABP is an equilateral triangle. And we know that all the sides of any equilateral triangle are equal to each other. That is to say, BP equals to AB. BP equals to AB. But according to what is given as the question, BB equals to 5. So we can write here that BB equals to 5. And from this equation, 5 equals to BP equals to AB. We derive that AB equals to 5. Those two sides of the equation are equal to each other. AB equals to 5. So the side AB of ABCD equals to 5 units in its length. You know that the of any square equals to the length of one side square. That is to say, it is AB square. AB is 5, so AB square is 5 square. 5 square is 25. So according to the second method, we have this square ABCD equals to 25 squares in size. So here is the second method. In the next step, I repeat on the solution of the first method, of the third method. Diagonal DB bisect angle ABC. This is the first half, this is 45 degrees. This is the second half, this is also 45 degrees. But this angle is 30 degrees, and therefore the missing angle must be equal to 15 degrees in size. In triangle BDP, 15 degrees plus 45 degrees, 15 degrees plus 30 degrees is 45 degrees. Therefore, this furthest angle must be equal to 135 degrees in size according to the sum rule. The sum of the angles in an triangle is equal to 180 degrees. So this is triangle DBP. We defined side AD is x, so therefore side AB must be also equal to x units in itself. This is, of course, a right angle because it is a square. We implemented the Pythagoras theorem on this triangle DAB. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. So in this triangle DAB, dB squared, that is the square of the hypotenuse, equals to AD squared plus AB squared. Again, dB squared equals to AD squared plus AB squared. dB is the missing side, so limiticity. So dB squared equals to AD squared. AD is x, therefore AD squared is x squared plus AB squared. AB is x, so AB squared is x squared. So in total, dB squared equals to x squared plus x squared, that is 2x squared. dB squared equals to 2x squared. Here we took out of this equation, and we found out that dB equals to the square root of 2 times the square root of x squared. The square root of x squared is x, so in total, dB equals to the square root of 2 times x units in its length. In the next step, we implemented the law of sines in this triangle DBP. Actually, the law of sines is true in any triangle, therefore we can implement the law of sines in this triangle DBP. Okay, so from the law of sines, according to the law of sines, this is triangle ABC that could be any triangle. Side AB equals to C units in itself, side AC equals to B units in itself, side BC equals to A units in itself. This is angle BAC, this is equals to capital A degrees in its side. This is angle ABC, this is equals to capital B degrees in its size. This is angle ACB, this is equals to capital C in its size. Capital C degrees in its size. So in this triangle ABC, that could be any triangle, according to the law of cosines, the following equation is true. that A over sinus A equals to B over sinus B equals to C over sinus C. Again, A over sinus A equals to B over sinus B equals to C over sinus C. So we can implement the law of sines in our triangle DBP. According to the law of sines, this triangle DBP, DB over sinus 135 degrees equals to BP over sinus 30 degrees. Again, DB over sinus 135 degrees equals to BP over sinus 30 degrees. And again, according to the law of sines, in triangle DBP, DB over sinus 135 degrees equals to BP over sinus 30 degrees. dB equals to the square root of 2 times x, and PB equals to 5. Again, dB equals to the square root of 2 times x, BP equals to 5. Sinus 30 degrees is 1/2, and sinus 135 degrees is square root of 2 over 2. So in total, square root of 2 times x over square root of 2 over 2 equals to 5 over 1/2. 5 over 1/2 is 10. Here we move the 2 to the numerator and square root of 2 to the denominator, so in total the value of this expression equals to the square root of 2 times x times 2 over square root of 2. We have square root of 2 in the numerator, square root of 2 in the denominator, so 2 square root of 2 get cancelled, so we left only with 2x in this side of the equation equals to 10. 2x equals to 10. Here we divided this equation by 2 and we found out that x equals to 10 over 2, that is 5. So one side of square ABCD equals to x and x equals to 5. Now that the opposite square equals to the length of one side squared, that is to say it is x squared. X is 5, so x squared is 5 squared, that is 25. So in all the three methods, we have to find out that the area of this square ABCD is equal to 25 square units in its size. Okay, thank you very much.